Okay, I think we can start. The next talk is by Emanuele Zappala, and he's going to talk about N-Lie algebras and the Yang-Baxter equation.
Yeah, thank you very much for the introduction. So I would like to start off by thanking the organizers for this great opportunity, and also I would like to thank all of you for attending this talk. And without any further ado, I'll go into the actual presentation. So this presentation is based on two articles, one of which has already appeared in on arXiv and is submitted, while another one is still ongoing, but it should appear hopefully in the next month. I suppose by the end of summer or at the beginning of the semester, the fall semester. One is with Victor Abramov, the first one from University of Tartu. The other one is from with Mohammed Elhamdadi from University of South Florida. So which part of the talk belongs to which is not really clear because things are a little bit fuzzy. So I will not mention, you know, what is in what article, but those are the main references. But there are also a couple of more articles that somehow constitute the backbone of the ideas of these two main ones. And one is set to appear in the Osaka Journal of Mathematics, and another one appeared already in Communication in Algebra with Mohammed Elhamdadi and Masahiko Saito. In a nutshell, there is a construction by Carter, Lisa Cranes, and Mohammed Elhamdadi and Masahiko Saito that associate to any Lie algebra self-distributive structure, and self-distributivity here is basically the third axiom that rack and a quandle satisfy. So the one that it's similar to the Reidemeister move 3. And you can construct an object of this type, and this method can actually be generalized to starting from N-Lie algebra, so a sort of generalization of the usual binary Lie algebra. And you can get a self-distributive structure as well of a higher arity, though. So all these definitions I will mention them. And then you can get from there is another general way to construct Yang-Baxter operators from the self-distributive structures. And then basically you can transfer the deformation theory of Lie algebra, which is based on cohomology of Lie algebras, the famous Chevalier-Allenberg complex, for instance. You can move everything to Yang-Baxter operators. And to do this passage, you pass through a cohomology theory, which is a generalization of the usual quandle and rack cohomology theory that was used by Carter, Kamada, Saito, Langford, and I think I'm missing one. There was another author, I'm sorry about that. But anyway, the famous state sum invariant based on two cocycles of quandles and racks, right? So you can generalize this cohomology to these structures, and basically I will work on the vector spaces, but in fact a good portion of what I'm going to say transfers to symmetric monoidal categories. So if you take a Lie algebra object and you do all the same business, replacing the equalities by commutative diagrams, you can just move on to symmetric monoidal categories and construct braiding inside that and define basically braided monoidal categories starting from a symmetric monoidal category. Of course, the target of all this discussion is to find the invariance of knot and links. And I will get to that unfortunately just at the end, because that's still the end goal, but we didn't get that far. So well, just to recall a couple of notions, an N-Lie algebra is basically exactly what you would expect in the sort of binary algebra generalized to n-ary operation. You see now here the brackets, they take n objects, so you have 2n minus 1 because the first n will contract to 1, and then here you will have other n more, n minus 1 plus 1n. and you can apply the bracket in nested one inside each other, exactly how you do the business, for instance, with operads. You concatenate operation to get higher operations in an operad. And this thing, it's replaced, this equality now becomes a sum over all these over all these things, that it's basically what the Jacobi identity would be if you started with a binary bracket. So there are very well-known examples of n-Lie algebras. For instance, the n+1 dimensional Euclidean space gives you an n-Lie algebra. So here n+1 and n of n-Lie algebra, they are the same n. So it's an exact construction with n+1 dimensional gives you an n-Lie algebra. And also you can take the bracket to be basically the formal Jacobian, the determinant of basically the derivation operators over an algebra that they're just required to commute. So of course, by Schwartz theorem, if you take, for instance, polynomials over the complex numbers in n variables, and the derivations are simply the partial derivatives, this thing goes through, and that gives a very nice example of n-Lie algebra. In fact, this was one of the main examples in the paper that introduced n-Lie algebras. That was by Filippov and appeared in the Siberian Journal of Mathematics. And before that, interestingly, they were actually introduced, the structures, in theoretical physics, because they were used to define higher order mechanics, so Hamiltonian mechanics with the n-ary operations. So basically Filippov rediscovered them and showed that what physicists have done basically was a sort of generalization of the Jacobi identity, because they didn't prove this property, but then Filippov was the one who formalized this whole thing. So since I mentioned self-distributivity, so quandles already have appeared in some of the talks recently, but I mean, very briefly, it's a binary operation. You have a binary operation on a set. The operation behave in this weird way, so it distributes over itself, exactly like the multiplication distributes over plus, but here it's having two different operations. It's the same thing. I want to point out something here. You see, there is the Z here, it splits in two copies. So this is important for what I'm going to say afterwards. And this corresponds to self-distributivity and Reitmeister move 3. And stuff that satisfy these are called shelves. And if the right multiplication is also bijection, this is Reitmeister move 2, and it's called the rack. And if, yeah, this is not power, it should be star, a mistake. If it's also idempotent, so it squares to the identity, everything squares to itself, then this is Reitmeister move 1, and this structure is called a quandle. Substantially, I listed them, you usually see them listed all the way around. I just listed them in cascade like this from 3 to 1, because a shelf that also satisfies this is a rack that also satisfies this is a quandle. So it's more natural algebraically to think of them like that. Plenty of examples, groups with conjugation. This is another case of Alexander quandles that I assume it's known to almost everyone in this in the audience, but it's good to repeat things. But the group with conjugation is really the epitome of the notion of quandle operation, and therefore also rack. So the generalization to n-ary structures, it's simply, you know, a matter of writing them down. It's not really particularly enlightening. So I skip directly to the categorical version. So you can think of doing this business in a category. So let's say you have a monoidal category, and let's say you This monoidal category is also symmetric because you have to switch the order. You need also a notion of co-multiplication because elements split exactly how that Z before that I showed splits in two. So you need a co-multiplication because you need to split elements as many times as you need in this symmetric monoidal category. And if these things, basically this is the self-distributivity property that I wrote there for binary, but this is the ternary version. Of course, the deltas, they have to be taken with the appropriate powers. Here, the powers get adjusted whenever T is an n-ary operation instead of ternary. So from now on, I will do everything for ternary because equations get out of hand very fast. So ternary already seems general enough. Whatever I'm going to say holds for n-ary, but you know, at least the equations are not excessively ugly as they would be with the n-ary case. So in the thing here, there is this shuffle. There is a very specific shuffle that it's used to order the elements. After you split all the elements a bunch of times as needed, you have to reshuffle things. As in the binary self-distributivity I showed before, you have Z that splits in two, but then you have to switch Z and Y to put in the appropriate thing so you can bracket things in the right way. So yeah, up to here, are there any questions or specifications that you would like to hear, or everything all right? Yeah, I'll continue. Well, that was a categorical version, but if you're working in the category of vector spaces, how it looks like self-distributive operation that is ternary is like this, where you use here, you see the Zwider notation to show that things split using the co-multiplication and are reshuffled. And then the ternary bracket basically here takes triples of elements. Here there is a sum implicitly considered over all the elements of the co-multiplication. Of course, in the case of symmetric monoidal categories, splitting with an element x into x cross x is exactly a co-multiplication. So it's simply, you know, sort of, it doesn't have a sum, so it's a simpler version. So if you will, the quandle with the Z that splits into it, simply a very easy version of this case. So the construction of Carter, Crane, Elhamdadi, and Saito basically takes a Lie algebra. It augments it with the scalar field, and it defined this co-multiplication that turns it into a co-commutative object in the category of vector spaces. And then you define this binary bracket, that this binary operation that uses the Lie algebra like this. And this turns out to be self-distributive. If you do it with ternary, I mean, there is not really much imagination up to here. You just, you know, do it with one more element and use the ternary bracket, and this goes through. You can prove that this thing works. You can do it also for n-ary. Proofs becomes, of course, much uglier because the equations get out of hand, but still. Interestingly, you can also have this operation. You can show that this is self-distributive as well, ternary self-distributive. And this operation comes from concatenating two binary operations, which gives you a ternary operation. In fact, this procedure we showed with Mohammed Elhamdadi and Masahiko Saito, that in any symmetric monoidal category, if you have an n-ary object and you concatenate it with an m-ary object, you get an n plus m minus 1-ary self-distributive object. So this is another way to construct ternary. So whenever you have a certain distributive object, you can go always in higher arities by concatenating as much as you wish. So, well, there is also a general way to obtaining Yang-Baxter operators out of self-distributive objects. These generalizes what you would do with a quandle, for instance. With a quandle, if you have x and y, you just switch the order of x and y, and what symbolically underpasses, the element that corresponds to the string that underpasses, gets multiplied by the other element with either star or star inverse. you do exactly the same, but instead of, you see, if X goes beneath Y splits in two copies, one goes on the left and one multiplies X. Here you have to use the co-multiplication and apply the operation as many times as needed. And you end up having a sum, and this thing turns out to be a Yang-Baxter operator, and you can do it for n-ary self-distributive structures. You need also a sort of invertibility condition, because for a quandle, for instance, you would use a star and a star bar, they're basically the dual quandle, but here you need some sort of invertibility, which it's this T bar called, and it's substantially the same, but it uses the formalism of Zwittler notation. So it's more similar to the contractions that you find, for instance, the theory of Hopf algebras, when you have involutions that basically kill each other. So very similar to star bar anyway, conceptually. And as you can notice, up to here, there is no mention whatsoever of dimensionality. So this thing goes through no matter what Lie algebra you take. So if you take something that it's infinite dimensional, it just works. I mean, there is no problem with that. You just need to construct your T bar, and everything goes through. So well, now we want a cohomology theory because we want to bridge basically the deformation theory of Lie algebra, which is known since the, I guess, 50s. So it's been known for a long time. And we want to bridge it to the deformation theory of Yang-Baxter operators. And we need to pass through a deformation theory of the self-distributive structures. Because you see, you take the Lie algebra, you construct your self-distributive structure, and then you get the Yang-Baxter operator. So to carry your deformations, you want to do through the cohomology, but you have to pass through self-distributivity. So you basically need to generalize the cohomology theory for quandles and racks to something for a self-distributive object. So categorical racks, if you will, or quandles. So it's it's not written in this case directly with its equation of operators. So instead of writing how they act on the single entries, actually the two co-cycle condition is written in that way, if I remember correctly. So you need basically something that behaves well with the co-multiplication. But there's no surprise because you have both an operation and a cooperation, so they need to be somehow, well behaved with respect to each other. The condition you need is this one that very much looks like a sort of co-derivation condition where the operation appears twice, though. So so you reduce from hom of X tensor 3 into X, you reduce it to things that satisfy this equation. And then the two co-cycle condition is, I mean, this thing doesn't really matter that much, but it's simply, you have to look at it as when you delete elements and you put them on the left-hand side of where they appear, then you apply them. Here, you are going to do it with co-multiplication. So you have to split the elements as many times as you need to apply them, and then apply them to the elements, and then you put it inside the psi. Interestingly, there is also the ternary operation appearing outside of psi, and this doesn't show up in the traditional quandle cohomology theory. You don't have, operation of psi of something in this way, but this is because of the deformation theory. So you want to do exactly like, if you remember the deformation theory of Lie algebras, you get basically the Cartan equation that has terms of this type with the binary bracket outside and then the psi inside. So this is the exact analogous terms, analogous term in this in this construction. And the second cohomology group is the usual business, and it turns out you can prove that this does basically the job that you would like it to do. It classifies the infinitesimal deformation of the self-distributive object. So here infinitesimal means that I'm extending the ground field or ground ring into this formal power series, and then I'm quotienting by the h bar squared. And interestingly, so now you can carry out all the Lie algebra deformation theory. You can translate it into the deformation theory of self-distributive structures, and under very mild condition, like something that is satisfied under semi-simplicity, get an isomorphism of cohomology groups. So this is technically very much, you're basically translating all the deformation theory from Lie algebras to self-distributive object. It also gives you bad news because to some extent, because semi-simple Lie algebras have trivial cohomology. So this is not true, for instance, for nilpotent and solvable. They have plenty of cohomology classes that are non-trivial, but an important class of Lie algebras, which is the semi-simple one, will have trivial cohomology, and therefore the self-distributive cohomology will be trivial as well. So what you want to do at this point, something that is possible to do, is to deform also the commultiplication, because up to here, I was deforming only T, the self-distributive operation, but the commultiplication was fixed. I can deform everything, of course, so all the maps all together simultaneously and get more general cohomology and more general, perhaps, classes. Equations here, they take this weird form in operatorial form here. Phi is, I think, the 2 cocycle, and psi is the deformation of the commultiplication delta. The most important thing is that you get a cohomology theory in this case as well, so it's not really an issue. The point is that, of course, at this point, one would wonder whether, there are actual examples of these structures, because there are going to be a bunch of equations, compatibility of different terms, something that has to be a coderivation, has to satisfy extra compatibility condition. Could well be that you don't have any solution in this case. It turns out that you actually have plenty of non-trivial cohomology classes, both in the deformed case and in the non-deformed case. So this is, for instance, this is the non-simultaneous deformation, and you see that SL2 and SO3 being semi-simple, they get 0 because their cohomology dies. It's isomorphic to the cohomology of SL2 and SO3, which is 0, as well known. And the same thing in the complex version, SL2 and SO3, they coincide, and then this is Bianchi 8 in the complex version, and still 0. But you have plenty of classes that cohomology groups that are non-zero in general. But if you pass to the simultaneous deformations, you have a lot of possibly non-trivial cohomology classes. So you have a lot of cocycles and deformations of delta as well. So you can deform both T and delta. This is the phi, the 2 cocycle for the self-distributive operation. This is the cocycle for the commultiplication. Technically, you can even deform iota, this is the co-unit, right? And there are a lot of free parameters, of course, both in complex and real case. So you see, it also happens that you can deform the co-unit non-trivially. Interestingly, of course, with Mohammed, we went to look at SL2 because this has trivial cohomology in the case of non-simultaneous deformation. So we went to have a look at this one, of course, for the simultaneous deformation, and this has, in fact, basically dimension 8, the cohomology group. So it shows that once you pass to simultaneous deformation and deform the whole structure altogether, you can get even the semi-simple case stuff that is deformed non-trivially. And this is almost the end, but basically you can construct Yang-Baxter operators from the deformed structures through the cohomology of self-distributive structures, and you get deformations of Yang-Baxter operators. and you effectively get a map from self-distributive cohomology into Yang-Baxter cohomology. And this is very useful because in the case that you have trivial center for L, this is isomorphic to the Lie algebra cohomology, and you get a monomorphism into the Yang-Baxter cohomology. So basically, you have a very principled way of taking a Lie algebra cohomology and stick it inside the Yang-Baxter cohomology, which is not necessarily a trivial thing, because in general, computing Yang-Baxter cohomology is a very, very difficult task. So it's usually done by basically computer. But this is a nice way of doing this. And for Yang-Baxter operators, of course, of a certain type. So you can wonder about higher deformation. So this was the infinitesimal case. In fact, for the Lie algebra is very well known that you can, the higher deformations are controlled by the third cohomology group. So if this vanishes, you can deform the Lie algebra as much as you want. And in fact, this is one of the obstructions is the Massey bracket. For instance, a discussion with Jim Stashev that appeared a while ago, he was asking me what happens in this case. I don't know yet, but what I expect is that you can transfer the Massey bracket from the Lie algebra to the self-distributive cohomology as well. And that would be an obstruction to deforming arbitrarily many times the self-distributive structure. Yeah. So this would mean that you have arbitrarily high deformations of the corresponding Yang-Baxter operator. So this gives rise to several questions, including how to control the obstructions in the case of self-distributive algebras. If you have an infinite deformation and you take the Yang-Baxter operator and you consider traces of links, do you get non-trivial invariants that are powers? There are basically power series invariants of the link. So you know that it's going to be invariant, but you don't know if the power series is actually trivial or not necessarily. So it's good to go and look at these examples. Can you do it with homotopy Lie algebras? So homotopy Lie algebras have all the n-ary operations all put together in a compatible way. Instead of choosing an n-ary operation and doing this, can you do it with all of them simultaneously? So can you get an opera that controls the deformation theory of the Yang-Baxter operator and construct the corresponding link invariants? Would it be trivial? So there are nice questions. So the bottom line, of course, is answering this question and saying if this theory is also only an algebraic theory, or it also has implications in knot theory, and it produces non-trivial invariants. So I'm 3 minutes over my time, so I apologize for that. I guess, yeah, this is the end. Thank you. Thank you very much.
Thank you very much. Are there questions?
Yes.
Mm-hmm.
I have a question. Yesterday's talk, there's a notion of cozoid, so tri-bracket. And is this related to your talk?
Actually, yes. The tri-bracket is related to the, actually with this operation, we studied it a lot with Masahiko Saito. Lately, we called it heap operation because we found that I think Wimberg and Wagner back in the 70s studied this operation, called it heap. So you take 3 elements in a group, you multiply them, taking the inverse in the middle. So you have x, y, z, and you take the y to the -1 at the center. And this thing, satisfies those properties of the tri-bracket, if I'm understanding correctly your question. So you can get examples of ternary self-distributive operations like these. However, I studied some properties of these things in the symmetric monoidal categories, but with Hopf algebras. So you start with the Hopf monoid instead of a Lie object, and you can construct a heap version, you know, a quantum version of the heap operation that should be a sort of categorical version of the tri-bracket. With Lie algebra, I'm not sure how to do that, but they satisfy the underlying condition that it's the self-distributivity. So yeah, I hope this answers your question.
Is there an analog of the Drinfeld double construction in the category in which you're working?
I wonder this thing. I don't know actually. That has been a question that I had for a while in my mind already. So yeah, I would like to. I mean, I wish I had an answer, but unfortunately I don't. But yes, because you can work with the Hopf monoids, so you can ask whether, you know, if you do this construction and you do the Drinfeld double construction, you know, if there is a relation. But I never double checked. So yeah.
Other questions?
Thank you for interesting talk. I have the following question. It's well known that if you have a set with one binary operation which is self-distributive, then we can construct the solution of the Yang-Baxter equation.
Right.
Yes, and now you are consider ternary operation, and it's natural to try to construct solution for the so-called tetrahedron equation. Tetrahedron equation is generalization of the Yang-Baxter equation. Do you know some concrete solutions for the tetrahedron equation?
No, actually, yeah, I never thought about it. Actually, that's a very good question. Actually, it's interesting to try. I don't know if these things they give rise to solutions to the tetrahedron equation. I should try though. Yeah, I think I will. Yeah,
Okay.
unfortunately, I don't know, but yeah, it's a natural question to see if you can get a ternary operation, or you know, you can do also the higher versions of the equations, for instance, and it's natural to say if you take a quaternary operation that is self-distributive, can you go in higher dimension in the hierarchy of you know, tetrahedron and so on. So
yes,
that
you
would
are
be
right.
interesting.
It's possible to define the n-simplex equation for arbitrary n, but it's not so easy to find solutions of it.
Right.
Okay, thank you.
Yeah, I mean, no, thank you very much for your question. Actually, in light of what you're saying, if you had a principled way of constructing solutions in this way, that would be very good, because there are plenty of families of examples of n-Lie algebras. So if you know how to take an n-Lie algebra and construct a solution for the n-simplex equation, that's, you know, that's useful, because it's not easy to solve it.
Yes, but it does not work in this situation, because we tried to do it. You can see our maybe preprint in archive is dedicated to n-simplex equation.
Ah, okay.
Yes,
Yeah, I'll surely take a look.
Lie algebra, Filipov Lie algebra does not work here, unfortunately. Okay, thank you.
Yeah, thank you very much. Thanks.
Other questions? Okay, I believe that the next talk will be at 3 o'clock, and we're all on lunch break until 3 o'clock.